Okay, now let's understand the convolution codes with examples from the given textbook. We have the similar idea what we discussed till now with the last video, stating that the convolution codes are a bit different from the block codes because they have the memory associated. So it says that it gives n digits generated by an encoder in a particular time unit. Uh, Not only it depends not only on the k messages but also on the preceding m minus blocks of m minus 1 blocks of message digits. It means that not only the present input, also on the past inputs, which is nothing but m minus 1 blocks of message digits where m is greater than 1. So usually k and n are very small. Now you like block codes, convolution codes are designed to detect or correct errors. Usually we say block codes are better suited for error detections and convolution codes for error corrections. So encoding scheme in the convolution encoder is designed basically using shift registers and several other practical procedures. So encoding is done usually with shift register, and decoding concept is with various decoding procedures. As we discussed earlier in the videos, we mentioned what all types of decoding. There is a sequential decoding, threshold decoding, and the viterbi decoding, which is maximum likelihood decoding. So that procedure is employed to have the decoding purpose. So encoding is only the shift registers. It is referred as linear sequential circuits, are referred as encoding circuits for the convolutional codes, and sequential decoding or test threshold decoding or viterbi decoding are the decoding circuits for the convolution codes. So as we said, k message bits along with m minus 1 previous message bits leads to the code block, which is convolution codes. That's the picture shown here. Please remember it is represented as n comma k comma n. A similar idea where constraint length is nm digits. Please remember m is memory, n is outputs, nm represents constraint length. What is the length of the code? The length of the code depends on nm digits. Now we can say the rate efficiency is k by n. So please remember in block codes we have the particular length defined for a particular code. Here constraint length is there n into n, n into m. So m is the memory. So that's the representation which is shown here. So the encoder circuit, which is designed in a simple way, can be shown like this: 3, 1, 3 convolution code where n is equal to 3 leads to 3 adders, k is equal to 1, which is the normal definition. K can be 2, 2 can be pushed in, k can be 3, 3 can be pushed in. That's the meaning. Now one bit at a time can be pushed in into the shift registers, and we have m is equal to 3, so 3 shift registers. The code is shown and the operation of the encoder hence can be explained. So let us come back to this. Okay, so let's understand this diagram what we have shown. In general, n comma k comma n convolution code, clearly understand n is the number of outputs of the encoder, which is nothing but the number of modulo 2 adders. Where k is the number of input bits entering at any time. Please understand, k is number of input bits entering at a time. If k is 1, 1 input bit enters at any time. K is equal to 2 means 2 input bits enters at any time. M is equal to uh, number of stages of the shift registers. It's nothing but the number of flip-flops. So m is equal to 3 means 3 flip-flops. M is equal to 2 means 2 flip-flops. Similarly, I have L, capital L, which is very important for understanding the generator matrix. That's what L is, number of bits in the message sequence. For a particular block, what we say, what is the number of bits in the message sequence? We have constraint length, which is m cross n digits, and rate efficiency k by n. So this is an encoder which is already been developed, which you can see what kind of output it generates. If we take n comma k comma m 2 comma 1 comma 3 as the convolution code, this diagram represents 2 comma 1 comma 3 convolution codes. So how we can say n is equal to means we have used two adders, n k is equal to 1, so input message bit is 1, and m is equal to 3, we have 3 flip-flops. So we have connected in some fashion in such a way that it gives C. But how they have connected, what is what, if you see, you will be able to understand how the codes are generated. Here most important things, as I mentioned in the last video, that understanding the generation of generator sequence. That generator sequence is nothing but in turn lead to the generator matrix. So how this generator matrix can be obtained, that is what the picture here. Now if you see this diagram, we have two adders. One we can call it as top adder, another one can be called as bottom adder. Let us understand. It says that the generator matrix, now the codes can be generated with various methods. What we said is, one is time domain approach, another is transform domain approach. Let us discuss first time domain approach. There are two ways to represent time domain approach. The second method we'll see, which is very easier, which is matrix method. The first method is with a set of equations. Now generator sequence is nothing but the impulse responses. So impulse responses leads to the concept called as generator sequences, which are represented as G1, G2, G3 up to Gm for the first one. So for the first adder, which I call it as top adder, generator sequences. For the second adder, I'll designate it as 2, but the sequences remain same, G1, G2, G3 up to Gm plus 1. Please remember Gm plus 1. M is the memory plus 1. If m is equal to 3, I will have G1, G2, G3, G4 up to that. Or you can call it as G0, G1, G2, G3 up to G3. Can be interlaced and arranged in a matrix form. The number of rows of the matrix will be L and the columns of the matrix will be N into L plus M. So it means that L cross N into L plus M represents the generator matrix dimension. So generator matrix dimension, which can be shown here, you can see this is general representation, L rows and L into N plus M columns, which can be represented as generator matrix. So this general definition of how to generate the code is represented as C is equal to D into Z. So you can observe it. So this represents Z generator matrix. And the equation, we know how to generate the code word. C is equal to D into G. D is the message sequence. Let's assume a block 10111 is the message sequence. Now G1 from the top adder is this, G2 from the bottom adder is this. How you can say 1011? So from the diagram, if you observe, the inputs coming from this is input bit 1 and no input from the flip-flop is going to the adder. Output of the second flip-flop is going to the adder. Output of the third flip-flop is going to the adder. Nothing is coming from the flip-flop 1. So it is 1011. So similarly, if you check for the bottom, 1111. All the four are present. That's what it is 111. That's what it is shown in this diagram. 1011 and 111 are the two sequences. Now how the matrix is written, since it has L 5 rows and L n into L plus m, which is 16 columns. Now you observe only two sequences are there, two generator sequences are there. They are written two at a time. So G1 G1 together, G2 G2 together, G3 G3 together, G4 G4 together. So you try to understand, G1 of 1 is 1, G2 of 1 is 1. So 1 1 column wise, if you see 1 1, 0 1 0 1, 1 1, then 1 1. Remaining sequence are filled with zeros to complete the columns. Now second rows plays a very important role. So I have added 0 zeros. So based on how many bits are getting in, that represents how many bits. So since we have 2 bits, that represents your message sequence, how many you are getting in. So similarly, if it varies, this shift also varies. So likewise, you can observe the continuous shift to 2 at a time leads to this generator matrix. So generator matrix generation is very simple once you know the generator sequence and M value. So now C is equal to D into G. This process we know: first row, first column, first row, second column, first row, first column, first row, second column. Each one is a column individually. Never bother about this spacing. Two together written because of we have two adders. So first row, first column, first row, second column. This continues. This is the code what we have generated. This is all about the convolution code which is generated from the given encoder circuit. So encoding of the convolution can be done using transform domain, wherein we have the impulse response, which is represented as the polynomial in coefficients with j number of modulo 2 adders. We define the generator polynomial with the equations like this. Very simple to understand. G0, we know that four terms, which is G1 to G4, which is 1011. 1011 can be represented as like this. 1 means 0, x is not present, x square is present, x cube is present. This is the equation. Similarly, G2, this is the equation. Whichever is present, that is the term. 1, x, x square, x cube, x4, like that it goes. This equation. So now the equation says that C1 of x, top adder output polynomial, can be represented as like this: d into g, d of x into g1 of x. Similarly, I have c1 of x, the multiplication, d of x is this, g1 of x is known, multiplication, 1 to 1 multiplication if you do, if two terms are repeating x cube, you write a single equation, no issue, after multiplying with the addition in between. A big equation if you write, identify x cube wherever is present. If two x cubes are there, discard them. 2x square are there, x square you discard. 2x4 are there, x4 you discard. 2x5 are there, x5 you discard. That is the property we already know, because if I say example x5, x5, if I take x5, if I take outside, 1 plus 1 leads to 0. So that is what the idea. This term will get cancelled. So x6 get cancelled, x5 get cancelled, x4 get cancelled, x3 get cancelled, x square get cancelled. So only remains this plus x raised to 7. Similarly, C2 of x, you cross check, this is the equation 1. Whoever get cancelled, this equation will remain. And finally, C of x is nothing but this is the formula which goes. We know that the final encoder output polynomial is given because n is equal to number of module 2. That's what x square comes into picture. So C1 x square plus x into C2 x square. Now x square is a term that we should understand, but this one is C1 of x. X square, when I say square it, so 1 plus x raised to 14. Similarly, C2 of x, you take square it, this is a squared one. So just add them with multiplying x with C2 x square, that we should not forget. This leads to this equation. Now, respective coefficients you take 1 from x. X square is not present, 0, x cube is 1, so x4, x5 is not present, that's what 0, 0, x6 is 0, x7 is present, 1. So like that you write from the equation. This is the representation. Let's take the same example, convolution encoder with information sequence 1 0 0 1 1, and find the output sequence. Time domain approach, transform domain approach. So what you can observe here, okay, in this example what you can observe, there are two top adders, two flip-flops. So you can observe this. So n is equal to 2 and k is equal to 1, and we have two flip-flops, m is equal to 2. So that's what G1, G2 can be easily generated. You can say top adder is connected with all the three inputs, bottom adder is connected with two inputs. So first top adder, all the three inputs, 1 1 1, bottom adder 1, no second input, and 1, so 1 0 1. That is how the generators are generated, 1, G1 and G2. You can observe the G can be generated with the help of L cross n into L plus m, which is I have L is equal to so many rows, and n into L plus m, that is 5 into 14. So it means 5 rows, 14 columns. So we have this representation. We know this is a generator matrix. So how it is, you know, so 1 1 1 0 1 1. So 1 1 1 0 1 1, remaining all zeros by 2 bits. So that's what the analysis continues goes. So similarly, we have C is equal to D into Z. This is what the code which is generated. Now similarly, we have transform domain approach in which D of x is there, G1 of x is there, G2 of x is there. The common output polynomial is dx into Gj of x. We can have C1 of x and C2 of x by multiplying the polynomials. This is what the expression will get. and the final expression c of x can be written like this. Ensure that squaring is done and the respective coefficients represents the output encoder result.